Hello everybody, welcome back today. And today we're doing all nodes distance k in a binary tree, which is LeetCode number 863. Let's get into it. All right, so I'm going to explain this on my iPad here. And so if we get started here, we see that we have a binary tree and we're given a target and a k value as our input. So what it's saying is we want to start at this target, which is 5 in this example, and we have this value k. So we want to find all the nodes that are distance k away. So in this case, a distance 2 away. How do we do that? So let's think about it, right? If we start at 5, if I draw a path from 5 to the 7, then that's a distance 2 away, right? Because there's two edges between 5 and 7. Same thing here. If I draw another path between 5 and 4, there's also two edges between that. But also, if I draw a path between 5 to 3 to 1, that's also two edges. So that's why our answer is 7, 4, 1, because those are the three nodes that are two distance away, right? So how do we go about doing this? Because our problem here is that in our binary tree, you can only go left and right. You can't really go back, right? In this case, where 5 went to 3 and then to 1, that's kind of a going back. It's going back to its parent. So that's the key. We want to go back to our parent. So if you think about it, a tree is just a undirected, or it's a directed acyclic graph, right? So if it's a directed acyclic graph, how do we use that to our advantage, right? Because it's directed. Well, let's try making it undirected, right? If it was undirected, then we could go back or forward. It doesn't matter, right? So if we can somehow, because this is how the tree kind of looks, right? If I draw these arrows, that's the direction. It's going down right here, left and right. If we can somehow make it such that we can go backwards for every node to go back to its parent, then we can maybe solve this problem with some kind of like a breadth first search approach, right? So let's try doing that. What if we do a BFS from the root? So BFS from the root, and what we're going to do is we're going to just do it normally how you have a queue, but we're also going to keep a map for the parents, okay? So what I mean by that is, let's just start with a BFS, right? So we push the 3 in, which is our root, right? And 3 has no parents, so we're good with that. And then we push the left and right children of 3, which is going to be 5 and then 2. Now, 5 and 2, since we're going to push the left and right children of 3, we know what the root is right now. So what we can do is we can go to our map and insert a 5 comma 3, and we can also insert a 2 comma 3. What does this signify? So this is the actual node, right? The children node. That is the parent of that node. So we're going to have a map. We're going to create a map with a breadth first search from the root that will have the node comma parent. And what that allows us to do is basically we now can go left and right, but we also know who the parent is. So if we know who the parent is, we can always go to that node, okay? So we're going to do that, and we're going to just complete the entire BFS. I'm not showing that all here because it's going to get large, but I can just fill it in here. So what I'm saying is we're going to have a, sorry, this should be a 1 comma 3 right here, but we're going to have a, we're going to have, we're going to then have 6 comma 5. We're also going to have 2 comma 5. Then we're going to have a 7 comma 2, a 4 comma 2, a 0 comma 1, and then 8 comma 1. So again, remember, these are the nodes and these are the parents. And that's what our map data structure will look like at the end, which is going to just contain all the parents, right? So that's what we want to do. Once we do that, now can we do a BFS? Now, the idea is, since this is an undirected kind of graph now, if you want to think about it that way, we can just do a BFS starting at the target node itself. So we start at the target. And why we're doing a BFS and not like a DFS is because BFS actually just lets us track the distance. Because in an undirected graph, every edge is just one distance away, right? If we do a BFS, if you think about it, the second level will be, in this case, the answer, right? Whatever nodes are on the second level will be the answer because that is distance 2 away from that target node. We can do a DFS because DFS means depth, right? So we're going down, down, but we can't really track of distance because I mean, yeah, we can't really keep track of distance because once you go depth in, then you might be interacting nodes that are farther depth, and maybe you could stop that, but it requires a lot more logic that we don't need because the BFS is just way more simple and also probably would be more efficient. So then the second step after this first step is to do a BFS from the target. So BFS from target root node, and thankfully they give us the node, like the pointer to it. Otherwise, we'd have to actually find the target using the value, right, that they give us, of the value of the node. But anyways, we have the node here, the node pointer, so we're going to BFS from that. So if we do a normal BFS from just that, right, in our case, we push the target in first, right, and then we can take this out, we push in the left and right children, so which is 2 and 6, right? But since we have this parent map, we can take advantage of that. We can say, hey, what is the parent of my target? Well, in that case, we go to this map, we go to 5 and see, okay, 3 is my parent. So I'm going to push that as well. So that allows us to essentially go left, right, and then up again as well, right? We do that, and then we move our distance. We're going to have a distance variable. We're just going to move it to 1. Now, another key thing when you're doing like undirected graphs is we need to visit it. So what we want to do is we want to have a visited map. And why do we need this? Like, what's the whole point of this? The reason we need this is like, let's say we start at 5 and then we go to 3, right? Now, the way that we set it up, left child of 3 is going to be 5. We don't want to go back, right? That's just undoing our work, which is no point, right? So we want to have a visited. So every time we push in a left and right child, we're just going to mark those as visited. So we visited 2, we visited 6, and we visited 3. All right. And I'm going to remove this curly brace because it's going to get cramped. But yeah. So we visited 3 because we pushed those children into the map. So then we go on, and right now our distance is 1. It's not equal to k. So we look at 2's left children, left and right. We're going to push 7 and then 4. And notice how we don't push 5 because we visited 5 already, right? So every time we get in, we're gonna visit the node first. So the initial node will be marked as visited always, right? So notice we don't push that because that means we're going back. There's no point in actually going back, right? So again, so we push 7 and 5. So this gets updated. 7 is true, 4 is true, right? Because that means we visited 7 and 4. And then we're gonna look at 6. What is my left and right children? There are none, so we don't really care. And then 3, what are the left and right children? Well, we don't go back to 5 again because that's visited, and then we push in 1. And then so now we say 1 is visited. And then we update our distance to 2 after this because that's the next level. But now we see that distance is actually equal to k, right? So if it's equal to k, this is when we break, and whatever is left in our queue is our answer. And as you see, 7, 4, 1 are left, which is exactly what the answer is, right? So let's get into the code now, and let's see how this is done. All right, so let's get to the code here. So first we need to find the parents, and also let me just mention, I'm going to be doing this in C++. Again, yeah, you could do any language, but I prefer C++, so I'm going to go ahead with that. So I'm going to set up that unordered map that we talked about, which is basically just going to have a key of a tree node and also a value of tree node. So I'm going to call this parents. And then to generate this hash map or unordered map, we can write a function here. So we'll write a function that just returns void. We're going to call it get parents. And it's going to take in this root, and it's also going to take in that unordered map that we have. But make sure to pass this unordered map by reference here, because in C++, we need to put this ampersand to say by reference. And that just ensures that we don't actually have to return the map or anything. We're actually updating this this actual data structure itself. So make sure we do that. I'm just going to have a check here to see if the root is null pointer. Probably don't need this here, but I'm just going to have it here. I think it just makes it clean. And then yeah, we're just gonna do a BFS, right? We're gonna do a BFS from the start which is the root. So I'm gonna initialize this queue. I'm gonna push the root into it, right? And then after we push the root, it's just a normal BFS. We're not gonna worry about the levels here. We're just gonna do normal BFS process where we're just gonna push the left and right children in. So here we're gonna do that. We're gonna take the front of the the queue, which is gonna be this way. I'm just gonna call it node. And then I'm going to pop it to make sure that we can actually get the queue empty at some point. And then we're going to check, does the node left exist? If it does, we're going to do something. And then if node right exists, we're going to also do something. And by something, I mean we're going to push it into the queue first. That's the first task. So we want to make sure that we're actually pushing these values in. So we're going to push node left, and then we're going to push node right as well. So I'm just going to copy this one here and push node right. But now the thing that differentiates this is we're going to make this parents relationship. So how we're going to do that is our key is going to be the node, and the value is going to be the parent. So how do we imitate that? We basically do parents, and then this is going to be the key, right, which is the node itself, and then it's parent, which is this part, right? Because we know that since this is the children, this must be the parent itself. So that's going to work like that. Same thing for here as well. It's just node right. And that should be it. That should be enough to get the parents relationship. So I'm just going to call this function here. Get parents, pass it the root, pass it my parents, and I have. Now we want to do a BFS starting from this target, right? So first things first, since we're kind of dealing with an undirected graph here, we're going to make sure that we have a visited array, right? Or a visited map here in this case, because what we want to do is we want to make sure that, for example, when we start at 5, we go to 6, 2, and 3. But once you go to the 3, we don't want to come back to the 5 ever because we've already visited, right? If we're doing that, we're undoing what we essentially did. So we're not going to find the k distance away, right? So we want to make sure we do that. And then we also want to have that Q again, right, for just a normal BFS. And then we're also going to have this distance, which is going to be our counter until we reach K. And then the first thing I'm going to do is going to push the target in, right? So make sure that you're not pushing the root in because we're not starting from that. We're starting from the target. And we also want to set the visited for the target to be true because once we put something in the queue, we want to mark it to be true, meaning that we've already seen it, right? So again, normal process, right? We do while queue is not empty. But in this case, we're also going to add this other case where it's like if dist is not equal to k. So this while loop is going to run until distance is not equal to k or the queue is empty, right? And we have that because once distance equals k, we know, and we talked about this on our iPad, that whatever's left in the queue is the answer, right? But if, let's say in this case where k is very large, we're not going to have anything in this queue, right? So we want to have an empty queue. So the queue will be empty. So that's why we want to get out of that when we can. So we do that, and then what we do is, since we want to make sure that our queue contains every level at a time, to do that, we need to actually do the size thing. So it would be queue.size, and then we're going to iterate through that size. So think about it this way. The size will change based on how we insert things into that queue. And every time we're done inserting, that's when we have a new level. So that's why we have the size value there. So again, we take out the front, right? So queue front, and then we also going to pop the front, right? So we can actually get to this empty case. Then we're going to check, does node left exist? Just like before, and does node right exist just like before? The new thing is like we can also go to the parent. So we're gonna check this parent node exists, right? Does this actually exist? So does this node have a parent? Because we can also go to that one. But another thing we need to add is we want to make sure we haven't visited them. So we want to make sure that this hasn't been visited. So this is how you do it, not visited, because the value is a key, or the value is a boolean. Same thing here, but for right, and also same thing here for the parent. So I'm just copying that in and changing these values. Make sure you do that carefully because sometimes it can, mess up. And then we're going to push those values, those nodes into the queue. And then also we have to make sure that we make them true, like the visited, right? Because same thing here, like we do. Every time you push something in the queue, you want to make sure you mark it as visited so that we never visit it again, right? Same thing for the next three as well. So I'm just going to tab these in just to make sure that we have it properly aligned. This was going to be right. And the last one's going to be parent. So that's how I'm going to access the parent here. So we push it into the queue, mark it as visited, and that essentially does our job for making sure that we actually have level by level. And at the end, just make sure after the for loop to increase the distance, because once we're done with that for loop, we know we're on the next level, so we can increase our distance from the target node. And at the end, we know after the while loop is like either our distance is equal to k or our queue is just empty. So here is where we're going to actually make our answer, right? So again, while queue is not empty, so if it's empty, never going to go in here. We're just going to have an empty answer vector. If it's not empty, right, we actually have an answer. And that's when distance is equal to k. So here what we do is we're just going to push back the queue.front, which is a node, but note that this is an int, so we're actually going to want the value, and then we're going to do queue.pop. So that's going to basically put every value in the queue into the insert vector, right? So if we run this, this should work as long as we don't have any compilation errors or some sort of like that. So yeah, it does work, and let's go ahead and submit and just make sure that we have it proper and we haven't missed any edge cases, and you see that it's accepted. So yeah, let me know down in the comment section below if you think you had any questions or you think that I'm missing something on the solution. But yeah, make sure to like this video, subscribe to the channel, and I hope to see you in the next one.